Okay, so let's take a look at problem number 416. And on this problem, this is module 4, we want to determine the resultant of the forces that we see acting on this pin connected tower that is down here, and then everything is all the way up here. So looks like there's a pin and a roller, a pin at J and a roller at A. We want to locate that resultant with respect to the right side here of the tower, which is from F to J, so along here. All right. Now, I gave I think, I don't know if it was a little hint, but just a suggestion that when you sum your moments individually, you want to go around point J, because you could either go J or F, but going around point J kind of takes a couple of forces out of the mix here. And then that just means you're going to locate your resultant times the vertical distance, which is going to be the Y bar. Okay. So our resultant, because we have individual forces that are going in the horizontal direction and a couple that are going vertically, we are going to have it, the resultant at an angle, and it's going to have an X and a Y component. So this one is probably the type of problem that has the most steps, if you would, but kind of the same process as the other ones. So as we look here, our first item is going to be drawing a free body diagram and oh no, we don't have to determine the reaction to the supports. We just want to, I'm thinking back, this is module 4. So we just want to know where the resultant is. So we want to figure out what is the resultant force of the forces that we just see here. So I'm going to show a simplified view or a free body diagram of what we have here to get started, and then we will kind of proceed. So this is problem 416. I'm going to put my convention, the upper left-hand corner here, including my moment. And then lost my, it's my straight edge here. Where did I put it? Well, I guess I'm gonna have to go without my protractor. That's okay. All right, I'm just gonna draw a vertical line and a horizontal line to represent that tower. This is point J. And you could show A if you wanted to, but the only things that we're really interested in is along this line from F to J, we have 4 horizontal forces. So we have 5 kips, we have 10 kips, and then 10 kips, and 10 kips. And then at the top here, we've got a vertical force right at F, 10 kips. And then at what is point E is going to be 5 kips. Okay. Now, distances between, so this is free body diagram, distances between. We know that the distance here is 10 feet. 10 feet, 10 feet, 10 feet, and 10 feet. I guess 10 feet between each one. Okay. Now, this is module 4, so you do not have to worry about the reactions to the supports. We just want to find out what is the one force that would replace all 6 of these forces and have the same net effect on the body with respect to, we want to locate our resultant on this line right here. Okay. So first things first, we want to find that resultant. Now, because we have forces going in 2 directions, we're going to sum the forces in the X and sum the forces in the Y to determine the X and Y components of our resultant. Okay. So step number 2 here is going to be, I'm going to call it the components of the resultant. Okay. And we are going to sum the forces in, I'm going to start with the X direction. This is going to be equal to the resultant's X component, not equal to 0. We're finding resultants here. Okay. So we're going to say, all right, sum our forces in the X. So we're going to take each one of our horizontal forces here, and we're going to add them up. So we're going to say, all right, our X is going to be equal to 5 kips. It's going to the right, so according to our convention, it's positive. Plus 10 kips, plus 10 kips, plus 10 kips. I think that's it, right? We've got 3 10s and a 5. So 3 10s and a 5. So the resultant x component is adding all those together. So we can see that that's going to be 35 kips. So Rx equals 35 kips. Now, this is a positive value. So that means that they're going to the right, which makes sense because all of them are, right? Now, this is not a final answer, so I'm not going to put a box around it. I'm simply going to put my little cloud around it, like an intermittent, okay? Now, as we look vertically, we've got a couple forces here. So we need to sum our forces in the y direction to get our y resultant component. So sum our forces in the y equals the resultant y component. So our resultant y component is going to be equal to, now these are both pointing down. So according to our convention, that's going to be negative, okay? So negative 5 kips minus 10 kips. So our resultant y component is going to be equal to a negative 15 kips. Again, not a final answer. Those are our two components, okay? Once we have those two components, we now can calculate the overall resultant, okay? So on the next page here, we're going to draw. So step number 3 is going to be our resultants, okay? So we know that, I'm going to go back over here, our x is positive, that means it's going to the right, but our y is negative, that means it's going down. So we are going to be in the 4th quadrant with our resultant, okay? So if this is the x, this is negative y, we have our resultant y component, okay? Our y is equal to 15 kips. Now here, I do not put a negative in front of that. The negative is because it's going down. So that's already, it's already taken care of. Our Rx is going positive, and that is 35 kips, okay, along the x-axis, okay? Now, our resultant is going to be the resultant of those two forces. Since they are x and y, then starting back at the origin, my resultant is going to point to the intersection right here, okay? I'm going to put theta here because this is a vector. So it needs to both magnitude, which is going to be the length, and it needs its direction. So the arrowhead and the angle. So we're going to get the magnitude of the resultant first by using Pythagorean's theorem. We know that this resultant is going to be equal to, because these are 90 degrees to one another, the square root of Rx squared plus Ry squared, okay? So R is going to be equal to 35 kips squared plus 15 kips squared. My resultant is, we get you get 38.08. I did not do a double check on that yet. So I will one more time.
Yeah, that's right.
Okay, yep, I got that. I got it again. So this is a box around, okay? Now, we're not finished. We know that it's going down and to the right, but what is that angle? So we need to find that angle theta. I'm going to use tangent. I'm going to use the two legs here. So tan theta is going to be equal to, if I look where theta is, the side opposite is the y component. So this is going to be Ry divided by the side adjacent, which is the x component. So that's going to be 15 kips divided by 35 kips. Our theta should be 23.2 degrees. Okay, and that's a final answer, okay? Now, this is the magnitude and direction of the resultant. We're not done yet. So we can put our box around that, but now we have to locate it on this line JF, okay? And this is what I was referring to in this right here. So we want to find the total moment about J that each of the individual forces make. And then we're going to set that equal to the resultant X component times that Y bar. So what we need to find now is the total moment that our individual forces create about point J. Okay. So I am going to, I think I should be able to do this. So my 4 is going to be summing my moments around J. Okay. And that's going to be equal to, so J is down here. And I'm going to look at all the individual forces, okay? And I'm going to find a total moment, okay? So there's not going to be anything to solve for. I just want to find out what is the rotation that's created here by the individual forces. So go ahead and write your moment equation, starting with any of these offset forces with their perpendicular distances, and find a total moment. And I'll do mine on the side here as well. Double check. Unless you got that same thing, Danny.
I'm double checking mine because I did not.
Okay. Oh. Now I got 850. Try again. Yeah, 850 is what I got. Negative 850.
Oh, I had the 5 times 10 feet is positive. I think that's probably why.
Oh, yeah. If we look here, this is gonna, oh, it is gonna go positive. You are correct, isn't it? Counterclockwise. Dang it. I missed that. Thank you. So then is it 800? Negative 800? Is that what you got?
I had negative 750. Let me see.
Those would be 3, 4, 5, 6,
Mhm.
7, 8, 750. I think you're right. Yeah. Yep, 750. Thank you. Oh my goodness, I can't believe that. I looked at it. Ugh, I should have put my finger and rotated. I looked at it. All right. So this is another intermittent. So we have the same number, right? Negative 750.
Yes.
All right. So now that we have that value, All right, we now are going to do our last step, which is going to be locating our resultant so that it has the same net effect, the same rotation that that moment did. So step number 5 now is locating the resultant. Okay, so we can say that the sum of the moments around J, and that's what we just calculated with a number, is equal to the resultant X component times Y bar. Why is that? Let's find out why. I'm going to go down here. So I'm going to redraw our little diagram. Okay. Here's our J. Here's F and here's E. Okay. What we did was we found out that our total moment around J came out to be negative 750. That means that the overall rotation due to those individual forces, okay, is going to go in this direction. It's going to go clockwise. So now what we want to do is we want to take our resultants, and we know that our resultant had a Y component, it had an X component, Rx, Ry, and then it was the resultant coming down here, right? The resultant at theta, okay? And what we want to do is we want to place this on that line so it has the same moment as the individuals did, all right? And so what we're going to do then to place it, this is going to be our Y bar dimension, and it's going to be perpendicular to the X component of the resultant. Does that make sense? Why this then? This is force times distance, force times perpendicular distance. So we take the X component times the Y value from J. Does that make sense? That's usually the part that's a little harder. So now we're going to put our values in here. We're going to say, all right, negative 750 hip feet is what we got on that previous step for the moment around J. It's going to be equal to the Rx component was 35 kips, right? So so this is going to be 35 kips times Y bar. We don't know what that is yet. So our unknown here is the Y bar, okay? So now I'm going to take my 35, I'm going to go on the other side. So 750, 35 divide, and I'm going to get a negative 21.43 feet is equal to, I'm sorry, Y bar. Now, this is where that negative, I always want you guys to hold your positive and negative values. But in this case, our negative value doesn't mean it's going to go down below J. All it means is that it is creating a negative moment. So you just want to ensure that the side that you put your Y dimension on, that it is going to rotate in the same direction as our moment, which is clockwise. And in this case, it does. It would be a dimension above J, and it's going to allow it then to rotate in that counterclockwise direction. So the positive or the negative doesn't really matter here. And that's your final answer. Does that make sense, Danny?
Yeah, it was that last part that I didn't really get.
Okay.
So that makes sense. Thank you.
You're welcome.